Now today we discuss the biasing. Okay, so what is biasing? So now today start the discussion of biasing. Okay, what is biasing? Biasing means some external voltage applied in that PN junction. External voltage applied on PN junction device. Okay, external voltage applied. So there are the two types of external voltage apply, either forward bias, another is a reverse bias. There is a two terminal biasing. Okay, one is a forward bias, other is reverse bias. Okay, so that's the diagram. PN junction device schematic P and N. Okay, so when P terminal connected to the positive terminal of the battery and N is connected to the negative terminal of the battery, so now the configuration is called PN junction are in forward bias. Okay, so here look at the diagram. So that's the internal configuration, and suppose we choose in p type material, that's the p type, that's the n type. Okay, and in p majority carrier be the hole. Okay, there is a hole, majority carrier hole. Okay, much more hole here, and less number of minority carrier. Here the minority carrier be the electron. Similarly, but in n type the majority carrier be the electron. Okay, majority carrier be the electron, and here minority be the hole, less number of hole here. And you see that configuration p type here, in p type, end of the p type, and these were connected by a metal. There is some metal deposited by that here in that region. Similarly here the metal are deposited here, and they create the metal semiconductor contact. Actually skip that part because this little bit complicated and these are out of our syllabus. Okay, that not included in our class 12 physics, that little bit complicated. Short kid out a metal semiconductor contact. Okay, let's skip that part, and now you can consider there is a metal here and metal deposited, and there is a p terminal connected to the positive terminal of the battery, and n is connected to the negative terminal of the battery. Okay, and here the p region. So this region is called depletion region or called space charge region. So here in space charge region we see that, so much more number of negative charge here, negative, and here is a positive. Okay, and this is a space charge region. Okay, and due to that there is create some electric field. Okay, in that direction electric field. And now p region. Okay, and p region connected to the positive terminal of the battery. So this electron move from p region to terminal and p gets more positive. Okay, so if p get more positive means more majority carrier in p region. Similarly, electron move in n type n region. Okay, similarly that electron in more majority carrier in n type region. Okay, more electron here. Due to that configuration, so concentration gradient for majority carrier in both sides, p type metal and n type metal, is more. So concentration gradient is more, and this is the variable. Obviously this battery is a variable, so concentrated gradient is more, so more diffusion. So here, So more majority carrier in both type of material. So more majority carrier in both material p type and n type material. So more diffusion. Okay, so means more diffusion means, so electron from n region to p region. Okay, and here the electron in minority carrier in p region. Similarly, hole from p region to n region, and you diffuse, and that the hole is a minority in n type material, hole minority in n type material. So here, due to that, is called minority carrier injection. Minority carrier injection. Okay, so minority carrier injection both a p type and n type material. Okay, and now if minority carrier injection more, and in this pasture region, suppose there is a negative, negative, and negative, 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 and has a more positive, and due to that electric field is less, and due to electric field is less means this region, bounded region, okay, is shrink. This depletion region will be shrink, width of the depletion region, obviously these are the width of the depletion region, W with a shrink. And when electron from n to p and hole from p to n, there is some barrier potential, we know that from previous class. There is some barrier potential and it's called V0, and that is a p type and n type material. And when apply voltage is more, so V0 now shrink, and now that shrink. For silicon, V0, that is a 0.7 volt. After crossing the 0.7 volt, the depletion width is much less, and these are carrier. Okay, mainly the diffusion is more, so majority carrier from P to much more diffused to N region, and majority carrier from N electron much more diffuse in P region. So due to that, we get a huge current after crossing 0.7 volt. After crossing 0.7 volt, that is that depletion with almost narrow, all negligible. Okay, now finally the diagram will look like this. That's the P region, that's the N region. Okay, region, and hole from P to N easily move, and electron from N to P easily move in that direction, and due to that we get a huge current. Okay, we get huge current. So V0 build barrier potential is much lesser. Okay, and we get current. Now the diagram, IV diagram characteristic look like this. That is a I and that is a V applied voltage, and suppose a crossing a 0.7 volt. Okay, before that this current is almost negligible, almost zero. After crossing these, we get huge current, exponentially huge current. Okay, we get huge current because the hole is much more move here. So more minority carrier injection here, similarly the more minority carrier injection, we get a huge current. So that is the forward bias curve, forward bias diagram. Okay, we get a huge current after crossing the 0.7. So you see that that is a barrier potential now is the negative. So you get a huge electron move from N to P, and hole from move from P to N is much more. Okay, so you get huge current, and this is almost exponentially high. Okay, so that's the key point. So diffusion current is too much increases, and depletion width must be less here. You get huge current. At similar configuration, when diode are in reverse bias, so the polarity will be reversed. So depletion will be higher, similar configuration, but the polarity should be reversed. Polarity of the battery, this is a battery, should be reversed. Okay, that's the junction forward bias. And now forward bias junction we get after cutting voltage, or it's called threshold voltage. Threshold voltage. we get exponentially huge current. Okay, so now in reverse bias, and I see that is a junction diode P and N. The polarity should be reversed. Now P connected to the N side of the battery and N connected to the positive terminal of the battery. So now the diagram is now look like this. That's the P region and N region. So hole is more in P region, less in N region, and electron less in P region, less in P region and more in N region, because the electron is a majority carrier in N, and now connected to the this configuration, negative terminal. Okay, so due to that configuration, electrons are situated here, positive here. Okay, so here you see that electron minority carrier are automatically in a P region, minority carrier. Okay, similarly, N region also generate more minority carrier. So due to that, the diffusion is less, and if the diffusion is less, and this width now increases, and electric field also increases. Okay, this electric field also increases, and if the electric field also increases, means diagram now look like this. There is some built-in potential V0, and we apply the voltage here, barrier voltage, opposite direction. So now the built-in potential is higher. Sorry, barrier potential must be higher. So the barrier potential is very high. So if barrier potential is very high, so diagram now is look like this. So a hole from P to N is little bit difficult. Similarly, electron from N to P is a little bit difficult. So you get a less amount of current. Okay, due to that less current means diffusion is very less here. Diffusion is very low, but electric field is high. More slope means more electric field. Field is high. Okay, and we get a width. This depletion width is higher or increases, and the jumping from electron from N to P region, there's a bounded here. Electron jumping from N to P, this is not possible here. So W be the increase, and we get very less amount of current. That's less current due to that minority carrier. The less current minority carrier means a drift current. Okay, so now that configurations look like this, the IV characteristics I V, so V now negative, and we get a less amount of current. Okay. So less amount of current here. Okay. And after crossing this, and if I increase the width is very high, after crossing some voltage is called breakdown voltage, reverse voltage. Okay, VBR, after crossing the breakdown voltage, so you get huge current. Then now that these are junction with a break, and we get huge amount of current, also called a burnout region, and we lost the diode. If I more slightly increase the VBR, reverse bias voltage, so you get huge amount of current and reverse current. Okay, and this current, this small current we get due to the minority carrier, due to minority carrier are called drift, due to drift, and the value, these values very low, low, and we get that this nonlinear graph. Okay, I will nonlinear graph. So if some hold VBR breakdown region, a reverse bias region, suppose if I call a 5.6 volt, and if increase the 5.6 volt, we get almost zero current, but after crossing 5.6 volt, we get exponentially huge current in negative direction. So that moment is a breakdown, means call a broken diode. Okay, the diode is born out. Okay, in that region. Okay, so apply voltage called barrier potential is very high here. If more potential, suppose we apply voltage V here, so this potential now V plus V naught. Apply voltage V, and here the barrier potential V naught. Okay, so flow from N to P electron is a blocking and similarly decreasing, and P hole from P to N also decreasing. Okay, so diffusion is reduced, and you get some minimum amount of current. Okay, and this minimum current due to that minority carrier. Okay, due to that electric field or minority carrier due to the minority carrier movement. Okay, due to that electric field, and is a drift current. So reverse bias voltage, after crossing this voltage called reverse bias voltage, and voltage called the breakdown region. When these are called reverse bias voltage, these are called reverse bias voltage, reverse bias voltage. Cause that breakdown region, we get a huge current. So diode are destroyed or overheating. Okay, that's a very important region. Okay, clear? And that's a reverse bias region, and this is called reverse bias region, and this is called a forward bias region. After threshold, we get a huge current. Okay, and one more question here. That question is and in that space charge region, okay, there is some changing conductivity here due to that electric field here, but in that P region and there's the N region, these two are the neutral region. Okay, these are the neutral region. When hole move from P to N, there is some when electron move. Okay, similar concept like a sodium. Suppose take an example. Atomic configuration is 281. If one electron less, so we get sodium plus. Similarly, if electron move from N to P, we get some ions here. Similarly, and hole move from P to N, we get some ions here. There is some ions, so that's why these two regions are the neutral region. Mainly, this junction is a conductive region. Mainly, the diode used for that junction. Without junction or without depletion region, we cannot use diode as a power device or semiconductor devices, because diode have property to the junction. That's why we use too much useful diode. Okay, clear? That's why diode is very important, and diode also have a rectification properties. Okay, so little time here discuss rectification. Diode have very good rectification property. So rectification means one direction, either positive or negative direction. Diode have only rectification property. Okay, so if there is a transformer, okay, and there is a AC source, AC mains, there is a primary coil and here is some secondary coil. Okay, and there is a diode, and there is some connected to the load resistor R. Okay, and you see that there is an AC source here, and AC sources look like this. These are the our AC source. Okay, and these are the AC source. Okay, these are the AC source, and when these are the for So these are the positive part and P positive and NB the negative. When positive terminal, a positive part of the AC source falls on P region, so P positive, N negative means that there is a forward bias. When diode are in forward bias, so the output voltage V naught look like this is a. So now diode are in forward bias, but when this negative N falls on P region and positive are in N region, so diode are in reverse bias, and you know that forward bias there is a reverse bias. So reverse bias voltage almost the 5 volt, and that is a 0.7 volt cutting voltage. So in reverse bias we get almost zero current, almost zero current. Okay, so that's why these are the flat region. There is a reverse bias. After falling a positive part, that's the input, as the output, we get diode again in forward bias, diode again in forward bias, and now negative falls here. So now these are the flat line, diode are in reverse bias, again diode are in forward bias. Okay, so we get there is a positive and negative here, but when output we get only positive here. So that's the one direction. So that's why this is called half wave rectifier. This is called half wave rectifier. Only positive part are there, negative part are clip. Okay, so these are called half wave rectifier, only one direction. Rectification means one direction. Diode have very good rectification property. Okay, so what is full wave rectifier? If diode have a rectification property one direction, similarly there is a full wave rectifier, and the diode easily convert AC to DC. So what is a full wave rectifier? Now the full wave rectifier is look like this. So there is a AC source, a transformer, there is a two diode here, and these are center tap transformer. Okay, and that's the full wave rectifier. There is a AC main source here. When that a positive part here. Okay, when positive part are falls on D1 diode, and there is the output. There's the input. When positive part falls on D1, there's the input obviously, D1 diode. So now D1 be the conduct, and similarly the positive part D1 positive falls here. So there is a negative terminal, actually look like this, negative here. Is a positive here, similarly opposite direction negative here. So now when that negative here, actually look like that is this, a positive here, negative here. So diode D1 is forward bias and D2 is a reverse bias. Okay, so D1 is forward bias and D2 is the reverse bias. So there is actually center tap means there is a 180 degree opposite here. That's okay. If there is a positive, that's obviously negative here. So now in first case, okay, here D1 in forward bias, and now this portion D1 is a reverse bias, Again D1 is forward bias, D1 is reverse bias, and here is same, here D2 in reverse bias opposite, and here the negative, so there is a positive, here is a negative, so this means positive, so D2 is forward bias. Okay, when D1 is forward bias, D2 is reverse bias. When D2 is forward bias, D1 is reverse bias. So D2 is a reverse bias, and if I combine these two, actually the whole output is a combination here, we get one direction, and there's a full wave rectifier. This is called full wave are in positive direction. Okay, there's a whole output are in positive direction, and here you see that negative portion is clipped here, but they are in positive direction. There's a half wave rectifier, and in that diagram or that circuit, we get whole D1 and D2 output are in positive direction. So that's why the total output are in one direction. That's called a full wave rectifier. Okay, that's our rectifier circuit. Okay, clear, that's the diode is a good rectification property, and some little bit change, we get some DC source here, okay, from AC to DC conversion. Actually that discussion jump to the next class, okay, that discussion with that important portion discuss in next class. So actually today in the class here, if you have any doubt what is a full wave rectifier, what is a half wave rectifier, what is biasing, any type of question, please ask in comment section. Okay, I will try to give the answer. Okay, so today in the class here, thank you.